Hello and welcome to seminar number 18. Today we are going to have a quick introduction into nuclear fission. So what's the plan for today? We are going to talk about fissile material, fission yield and neutrons from fission. So fission is just a fancy word for splitting the atoms. It's a preferred nuclear reaction with nuclides with a proton number of above 90, so thorium, anything past that is thorium. If you were to describe it in a nuclear reaction equation, you would use F for fission, so we have an XF reaction, and possible projectiles, so these X could be neutrons, of course we know neutrons, but there can also be some proton-induced fissions and alpha and deuterons and heavy ion-induced fission. We differentiate between low energy fission, so if the energy of the projectile is less than 10 mega electron volts, and high energy projectiles, so anything above 100 mega electron volts. But that's more in the topic of spallation, so XS reaction. Fission is just the opposite of fusion. So we have one big nucleus and this is split into two smaller parts, and there we have a release in energy. Fusion describes having two very small ones and fusing them into one bigger one. So hydrogen going into helium, for example. Fissile material includes the following radionuclides: uranium-235, which is enriched from natural uranium, uranium-233, which is bred from thorium-232, plutonium-239, which is bred from uranium-238, and plutonium-241. They can sustain fission. If you look at the neutrons released by nuclear fission with thermal neutrons, so the neutrons have a kinetic energy of 0.025 electron volts, you can see that the uranium-233 on average releases the most number of neutrons, but also a very hot candidate is the plutonium-241. In my opinion, plutonium-241 isn't really a good fissile material because first, it needs to have a high fission cross-section, so not plutonium-240 or uranium-238. And in addition to that, it needs to release 2 or more neutrons on average per fission. Of course, you could, in theory, grow the number of neutrons if the neutron releases is just greater than 1, but that's not for practical use. And it has to have a usable half-life. And this is not the case for plutonium-241. Even though it's classified as fissile material, with its half-life of 14 point something years, I wouldn't make a fuel rod out of plutonium-241, even if I could. If we look at fission in general, we can see this very awesome diagram from the Karl-Heinrich Lisa. It classifies the whole fission process into different phases. So we can see this target nucleus in the ground state, then excited by neutrons. Then we have a saddle point, a neck formation, and after that we have 2 different fragments separating, and then after this the primary fission fragments are separated due to Coulomb repulsion, so positive and positive, of course it's going to repel each other. And then after this we have the evaporation of neutrons. These are the neutrons that we are talking about, and so on and so on. And after many different steps, we are not talking about fragments anymore, but about fission products. And if we look at the fission products distribution here, we can see that we have 2 branches. One heavy branch at the mass of 130 to 140, and one lighter branch around the mass of 90 to 100. So not the whole periodic table is produced equally when doing fission. This is due to nuclear fission not being symmetric. Therefore we have one heavier fission fragment or product and then one lighter one. And this heavier one stays constant. If you look, you have uranium-235, uranium-233 and plutonium-239, but the lighter one shifts. And can someone have an explanation as to why this lighter branch shifts? If you look at it, these nuclides are formed at the first magic neutron number of 82. And the rest is just the rest of the mass of this or that fissile material. So uranium-233 is lighter, therefore the rest between uranium-233 and the first magic neutron number, 82, is just a bit less than from the mass of plutonium-239. Therefore, if you look at it, it shifts towards the higher masses if we have our fissile material being heavier. Looking at the fission yield, there is a number, the fission yield, and it only looks after the emission of prompt gammas from primary fission products, so not fragments. We have a number, which is the cumulative fission yield, and if you add all of the cumulative fission yield for every isobar, you get a number of above 200%. So nuclear chemistry is the only field in chemistry where you have a yield of above 200%, and you did something correctly, because you have one atom and you make 2 smaller atoms out of it. So above 200%. The above 200 is due to ternary fission. So sometimes it splits into 3 different fragments and then products. It also looks after the emission of beta delayed neutrons. So if you look at an excerpt of the isotope browser app, we can see this fission decay chain. So we come from a very neutron rich environment, indium 137, it does beta minus decay, beta minus decay, beta minus decay. Along the isobar, the mass doesn't change, and all of these ones will end up into cesium 137, and the production of cesium 137 is then described by this cumulative fission yield. So anything that will end up producing cesium 137 will go into this cumulative fission yield for cesium 137. As I said before, we have a shifting of the lighter branch. This is due to the heavier branch at the first magic neutron number of 82 and the lighter branch just being the rest. And if we were to do fission with fermium 258, there will only be one branch because this one shifted so much that they overlap and you just have this one big branch. And if we look closer, you can see a very fine structure for the uranium 235 fission. You can see that we have a relative peak at 100 here. So this is the red one, relative peak at 100 and 134. Why is that? This is due to the preferred formation of more stable GG fragments. Because if you have uranium 235 and you shoot a neutron into it, you will get a compound nucleus, uranium 236, with the even or gerade neutron number of 92 and a even or gerade neutron number of also some number, which adds up to 236. So from this even or GG compound nucleus, you get 2 preferred GG fission fragments because GG is always more stable than anything else. At the beginning of the presentation, I was talking about neutrons from fission. So there has to be at least 2 or more neutrons from every fission to sustain nuclear chain reaction. And where do these neutrons come from? They come from the primary fission products. So when looking at the energy distribution, we have some sort of the energy distributed to the kinetic energy of the fragments and some to the kinetic energy of neutrons and some other factors like the beta decay and gamma radiation and prompt gammas and stuff like that. But we have some kinetic energy of the neutrons. And if we look at the numbers, per additional 7.5 mega electron volts of excitation energy coming from the initial neutron coming into this fissile material. In this example, it would be plutonium 239, which forms the plutonium 240 compound nucleus. On average, we get 1 more prompt neutron emitted from it. So it is really important that these neutrons are released by the primary fission products, which means that the direction of flight is similar to this of the fragments. So you have this Coulomb repulsion, and after this, you then get the prompt neutrons. If we were to look back a whole while, we can see that they kind of did it correctly. So the neutrons fly out in this and that direction. Same with the fission fragments. It would be incorrect to draw the neutrons flying off in this direction and the fragments flying off in this direction, because the neutrons are emitted from these fission fragments. So good to you, German Wikipedia. Thanks for this animation. With that being said, thank you for your attention and goodbye.